All right, so let's get started. Good evening, everybody, and welcome to the last Twed of the spring 2019 season. It's a little unusual that we have a normal Twed after our Twed Lightning Talks, which was 2 weeks ago. Thanks again to everybody who participated. Just a little bit of logistics. We are streaming and recording again this evening. There are, as has been the case actually with several of our talks recently, there are a number of people who, if they don't watch it streamed, they're going to watch the recording of it. And our Twed talks are always easy to find using the Google. This evening, we're welcoming Telus World grad student Anirudh Prabhu. We're very excited to have him. I've been nagging him for a couple terms to do this talk, and he consented or gave in. So without further ado, thank you very much.
Thanks, John. So as you can see, what we're talking about, also I just noticed this, so please continue to ignore this for the next 2 minutes. The date is 2018, it should be 2019. All right, so the talk is about the Global Earth Mineral Inventory, or GEMI, as we're going to refer to it from now on. GEMI is the data legacy or a data repository or data inventory that we have created as part of our DCO efforts and as part of another project effort called DTDI. So DCO stands for Deep Carbon Observatory. DTDI stands for Deep Time Data Infrastructure. So our work on both of these projects led to the creation of this resource. So before I start, let me give you some context. In some of my previous talks and a lot of the other lightning talks, you keep hearing me talk about DTDI, a lot of the work we do with minerals, with fossils, with planetary data, and so on. So we published quite a few papers on that. So the context there is the mineral data resources that we used were from various fragmented resources. There are some like field standards or domain standards there, but they're all fragmented, and we constantly found ourselves in need to retrieve parts of data sets from various different places, put them together for analysis, and then do the actual analysis and gain the insights. So as we were doing that, we found that it's just best to have this assimilated, coalesced data set in one place and make it easily accessible for the other researchers who want to do this. So that's kind of what led to the creation of GEMI. To start off, let me describe some of the data resources, the major ones. So a few of the really important ones are RUF and MINDAT.org. Both of them are industry standards for getting mineral data. The other is the IMA, the International Mineral Association approved list of minerals. And there's also, as an extension of RUF, is the Open Data Repository, which you can't see very clearly here, ODR, which is also an effort going through. And a lot of the mineral data is actually in books and like whole scientific literature. The Handbook of Mineralogy in particular has really valuable data like geological parameters, including hardness, color, and any other geochemical parameters. So we'll explore this a little later. So that had also to be rescued and digitized, which we did. So to start off RUF. So RUF is an effort out of University of Arizona with Bob Downs, Dr. Robert Downs and his group in UFA. So they created RUF, which was initially for Raman spectroscopy data, but which evolved into a much larger data resource. So what you see here is an IMA approved mineral list, which has 5,000 plus species of minerals. You can filter it many different ways. What you see there is the mineral evolution database. When you click that button, it takes you to the MED, which contains the ages of these minerals, which have been kind of painstakingly rescued or extracted in a mostly manual sense by Josh Golden, who works at University of Arizona. They've been working on this for, I don't know, like 5+ years or something, where so when we met him, he'd already put most of this together with, I guess, many hours of his time and a lot of undergrads and grad students. So they look at all the localities where minerals are found and look through various scientific literature to find confirmed first occurrence, and like minimum age of the occurrence of that mineral. And then we can use that for analysis. Mindat.org on the other end is Jolyon Ralph's idea. It started like in the, I guess, the late 90s or early 2000s as his personal mineral repository as a mineral enthusiast. And it has now turned into like the biggest crowdsourced mineral data repository. So this is completely crowdsourced. People go find minerals in different locations. They take photographs of it. They learn about those minerals and post the data here. And so we have about 275,000 known localities. This is including not just minerals found on Earth, but some Martian minerals and moon minerals and Vesta and so on, and 1 million plus mineral locality pairs.
What kind of validation? They just take a picture?
So the validation is done by a team now working at Mindat with Jolyon. The picture is one aspect, but they also explore and add other parameters such as color, hardness, things that they can verify as just a mineral enthusiast or a gem enthusiast.
I'm sure they take a hand sample and do that.
Yeah. So part of the localities here are also used in rough, which scientists then use the minerals from those locations to do exactly what you're saying, to explore them, put them on an X-ray diffractometer, get the unit cell parameters. All these things are done, but not as part of Mindat. But the data set, locality data set from Mindat is also used in rough, but they only look at IMA-approved minerals there. Another data set that sort of came about as part of our work in the DTDI project is what we are now calling Mineral Properties Database. Name, we haven't really fixed a name yet, but this is what we're calling it for now. It contains many more geological parameters than are available in any of the other big data sets. So the goal of this was to find as many geological parameters which we can understand and learn patterns from, also to understand multi-dimensional or multivariate trends among different mineral species. So you see, like, more than, so from mineral evolution database and rough, you just get age, you get other basic stuff like color or redox state, but you get method of discovery, structural complexity, and like many more columns. I'll show you a screenshot of that later in the slides. So far, Shauna Morrison, the science lead for the GEMI effort, she compiled the copper data set for the mineral properties database, and Sam Perry from Notre Dame compiled the same data set for uranium minerals. Both of them were started as an effort to improve their own research into these respective minerals, but now we're putting them in GEMI and expanding this. So future goals of this include like going through all the elements in the periodic table. So we're working on chromium, vanadium, and manganese right now to increase the data sets size. So data collection method, this is a pretty generic slide I just wanted to throw in. So most of the data set, most of the research, there's some need to go out into the field and find these minerals and explore them, and then look at them under like various machines to get these geological parameters. But a lot of this work has already been done by a lot of scientists, and there's a lot of published work out there. So we can use that published work to directly compile a mineral data set. So that's what's been done. Mindat is crowdsourced, as I mentioned earlier. Other data sets have like APIs that we use to extract and put it together. And there's some data rescue that's happening, which through Python scripts and R scripts that look at PDFs and use the information in the PDFs to create an automatically processed data set. So this, as I mentioned earlier, is a page on the Handbook of Mineralogy. So the Handbook of Mineralogy is like pretty well formatted even for a PDF document. One page each per mineral. So this is acuanite, and you see the complexity there. So you see a point group in the crystal data, so crystal complexity. You see physical properties, optical properties. You see the chemical properties, chemical composition of it, and you see occurrence, association, and distribution. So we were able to extract each one of these features, compile them in a data set just to the Python script, and this gives you a ton of very useful and valuable information. So this is a pretty big contribution to the field because they were individually going and only extracting the minerals they want, and now they can do it much easier through Gemi. So as part of Gemi, what we wanted to do was not only compile this data set, but also make it available to the community in a pretty easy manner. So what we did was put together an information model. I can't read it. So let me just explain that. It's clear there, right? Yeah. So the information model basically looks at the two entry points for the Gemi browser. One is the mineral point. Oh, no, never mind. I was looking at this. There's a pointer. So the mineral browser has all the important geological parameters for minerals, which you can do a faceted browsing by, and you can extract exactly the columns and rows that you want and download it into the required format, and then use it for analysis. And the second entry point is the locality browser. These two are highly related. So the locality is, so locality contains certain minerals. Minerals are found in certain localities. So, and for the localities, you have other locality-based parameters like rock type found there, number of minerals found there, lithology of the locality, age of the entire locality. So typically, when you have a mine, all the minerals found there have the same age. You also have tectonic settings around that area and geological address of their locality. Similarly, the mineral has much more rich geological parameters. So you see method and year of discovery, maximum age, paragenetic mode, a lot of features related to crystallography. You also have the chemical and the physical properties. So
how much of that terminology did you make up, and how much are you reusing from existing ontologies?
So everything is being reused from existing ontologies. There are some terms here which haven't fully reached consensus yet among the community. One of those would be this main term locality, as to what defines a locality. So we, a group, have formed a working definition of that term as well, and we're trying to put it out there to get more people to agree to it or discuss it. But everything here, none of it is new from our side. It's all established terminology, and it's widely accepted in the community. Okay. So this information model.
Actually, I'm sorry, just get a follow. I was going to ask that question, so I'll go follow. So yes, it's accepted, but is it accepted in the sense that you're getting those from SIO?
Oh no. So yes, that's not. It's not accepted in that sense because there's not many other outside of tweets the ontology, and what was the other? There was one more. There's not a lot of geology-based ontologies as there is in health informatics or biology. We have, these are just accepted definitions to be used for terms in the field in publication and in.
So we're creating an ontology for this work, but it's based on standardized terms.
They're all just common geological terms, some of them going back hundreds of years, actually.
Yeah. So these are accepted definitions for the vocabulary. There's no existing ontology that uses it.
So you inherit from Suite and Geon, maybe geology ontology.
So we haven't created this ontology yet. So we are part of the Gemi is going to be to create this. So far, the demo I'm going to show you simply uses Elasticsearch's JSON format. We haven't used RDF for the Elasticsearch yet, but that's one of the steps we plan to do before October. But there's a method established to do that, which we've done for DCO in the past, but we haven't done it for Gemi yet. But that's one of the future tasks. So we haven't imported anything yet, but the plan is that there's only a few established ontologies which we plan to import from, which will have some of these features, but not all of them.
I was thinking that your color coding might be the different ontologies that you were inheriting from.
Actually, no. This is just the color coding. This is a mind map, and the color coding is by level. That's all.
Oh.
So we use this information model, and so the backend is coded using Elasticsearch, which is a distributed search analytics engine. Most of us, I guess, are pretty familiar with Elasticsearch. You can provide access through an API. It accepts JSON input. It has a little funky JSON that it accepts. It doesn't exactly accept the JSON that we know. There's a few specific kind of features that are
You
required
have
for the
to kind of
JSON.
spoon feed it.
Exactly. So obviously to do that, we have our Python script that converts any text delimited text files or tabular files into this JSON format, which we can automatically do. We also have a script, as I mentioned, to do the same thing for RDF files, which is why the next step is to create an ontology where we can create an ontology based on the information model here, and then use the RDF and directly load it in. So that's the next step we're going to do. And the front end is built using Facet View 2. Both Elasticsearch and Facet View 2 were the same things used in the DCO data browser and like widely used in the DCO website in general. This is a faceted browser interface, uses data residing in Elasticsearch and mainly built using JavaScript and HTML. So this is pretty straightforward. So here's an example of the interface. I have a link to the actual initial demos we created. So what you have is a simple DCO browser. You have Mineral. This is a Mineral browser. So you have Gladite and all the geological parameters that we want to look at. So you have chemistry, color, hardness, paragenetic mode, maximum age, ICSD code, and localities where it's found. You can then facet by those features that you see on the left, which are mineral, paragenetic mode, color, and hardness. So you can facet by and search by exactly what you want. The elements are the things that are most searched by in the beginning. So you want to see what has copper and hydrogen or copper and sulfur. And so you would say so copper and sulfur, Gladite would come up. This has copper, sulfur, it has lead, And so at the end, you export it into whatever format you want. At this point, we're just doing text delimited exports for most people using Python or R-based analysis. But we plan to expand that as well in the future. And you can then search by whatever query you want. And so
could you actually, so any one of these, okay, I guess you've done it here.
Mhm.
You've got each of the.
I said copper and hydrogen here, and the color should be green. And so it gives you a list of 73 minerals right now in whatever small data set we've loaded up into the demo. And you're able to export the results into this kind of a file, right? So what it gives you is all the parameters that exist there: the name, the chemistry, chemical formula, redox, paragenetic mode, volume, and the color, luster, and hardness.
So can you kind of look at this, and is this an example that's showing information that's kind of coming from different data sources?
Yes, it is. So so there's couple. So the name, the chemical formula are coming from the rough IMA list. Luster and hardness and color are coming from the Handbook of Mineralogy. Paragenetic mode, volume, and redox state are coming from the mineral properties database that I described, which was created by individuals for their research.
And do you have the provenance in there? So can I see that if I dig in?
So you will see so far the provenance for the columns is not fully put. I'll show you in the demo. It shows you which rough ID or the Mindat ID that it's coming from, and we've linked it there in the demo. So you'll be able to trace back to the original pages. We haven't done it for the mineral properties database because it was just a CSV that was provided to us. So we're still working on implementing that ID into rough, but it will be there because the data citation mechanism that we use works off of each contribution having fair credit, which I'll get to later in this time. So it will be there, but
If you're going to answer this later on, stop me. But do you have a way, especially on color, for handling situations where the same mineral can have different colors, multiple different colors?
Yes, but same minerals don't typically have multiple colors. They have one established color. If you have multiple colors on a rock, it typically means you have multiple minerals in that sample.
No, but there are pure mineral species that have different colors due to impurities. Now, you may want to just define that as a separate mineral, which you can do. But then there are some minerals that have different colors simply because of the stress regime that they're under, which is exactly identical mineralogy, but stress regime. I mean, calcite, notorious example, it can be powder blue, or it can be basically clear or milky white.
So the method that we use has a place for multiple mineral colors, absolutely. The colors that we're using are only used, are from the handbook of mineralogy. So each mineral is assigned like one color, and we just end up using that. So whatever colors you see here is what we use. If there are multiple, there is place for multiple in the information model for sure.
So how would you represent this sort of exception?
Oh yeah, okay. So yellowish if coated by lemonite. So typically this exception we didn't take into account because it says if coated by limonite has its own color and acuminite has its own color. So we just want the original colors for each of these.
Okay.
The interactions would, at least at this point, are not part of GEMI, but that's a good question to bring up. I'll bring it up to the group and see how they want to.
Well, and it looks like you have two colorless, two colors there, colorless
and white. So if there are two colors like this, then we will, there is place for that. Yeah, it's just going to be separated and you can search by them. So the way Elasticsearch works, as long as it's comma separated, even in a single column, then it'll separate and search by it. So it'll show up both in white and colorless as you search in a faceted manner. So like I said, the methodology is in place to handle this. That's in fact how the elements work in the first place, because you have multiple elements showing up here. And like, as long as they're comma separated in the back end of the data from the chemical formula, it'll show up there, individual elements present. So the method will work, yes. So yeah, so you can export it and then use it for analysis. So that's the example. So
it's interesting, kind of as you've described it so far, it's kind of like you've taken a development strategy of kind of prototyping something that works first, and then thinking about kind of the semantics
yeah, because like
that stuff.
There's a lot of need for like people just using this data and need to put it in place. So we thought it's good to quickly prototype and then like we make it more robust as time goes. But yeah.
Well, having dealt with a lot of those people for a few years, I understand.
So let me think.
I just think that what's Jesse's common quote is perfection is the enemy of the good. Yeah.
So I'm just going to bring this over.
That's assuming they have a good ontologist perfection.
So these are pretty initial prototypes.
So we're looking at the live thing now.
This is the live thing. This is on the DCO test instance, but this is very initial, not as much. But like I said, so you have this data set. What I have added since the screenshot, or what Ahmed has added since the screenshot, is this kind of ID in place. So like I said, the minerals themselves are coming from the rough IMA approved list.
So can I ask?
Yes.
So do you have DCO IDs for minerals?
No, we don't have DCO IDs for minerals yet, but this is the first actual data legacy that is working on
But
DCO.
will you?
So we will have DCO IDs, but I don't think we're going to plan to have it for minerals, but for contributions as contributions, that is the granularity. Okay. So rough as a contribution is going to have its DCO ID. GEMI as a whole will have its DCO ID. I'll talk about that in the later slide. It's going to come up. So like I said, so like if you look at, you click this, it takes you back to the original source of that, and you see the provenance here as well of where they found it from. So each mineral has an ID like this, where you can trace back where it came from, where was the original source of the mineral, and you should be able to do that. And you can search, like I said, in a faceted manner to say hardness of 2.5.
So these are instances of those samples, is that right? Or
these are mineral. These are not samples. So when you say sample, you mean one sample of a mineral found at a particular locality.
Yeah.
This is generally true for the whole mineral across localities. That's why when it says localities, it provides multiple localities.
But can you pull up individual instances? Can you go?
Yeah. So that would be the So that would be the locality browser.
Oh.
So these are connected in this manner. There's like 2 entry points, right? Okay. So this one locality has only one mineral. This locality has 3 minerals. So if you want to look at this locality, you'll click the ID. It'll go to Mindat, where all the locality information is stored.
Okay. So that's kind of cool. That this is sort of a meta.
This is a meta. So that, like I said, there are established resources that have been used by the community for years, but they were still pretty fragmented, and there needed to be, like someone to coalesce it and to make it available. So yeah, so you see, this is that locality with the individual minerals found at that site.
Yeah.
You see the features of that locality and how they were collected, and other mineral-based features as well.
So now,
Yeah.
making this work is, Mindat had to stand up an API, Rough had to stand up an API. They already
Rough
have
has
other,
Yeah, so Rough has not so much an API. They have a relational database that we can access.
oh, okay.
Mindat is a little more closed. We are having discussions with Jolyon, because so far it's worked like you get permission from Jolyon for particular usages, and you use that data for your research. So we need to have something in place
But these
for
guys
that
have
to be a
been,
little more smooth, you know?
so DCO's been going on for almost 10 years,
yeah,
right?
yeah.
And these guys, some of these guys have been going on for
More than 10 years, like almost
more than 10 years, but in the context of DCO for all that time. So
Right.
they've known this stuff has been,
So I don't think like these cases especially have been involved since the beginning of DCO. They have been involved with collaborating with us since the beginning of the DTDI project, which was 2016 for us, or 2015. Each of Mindat and Rough and these sources come with their own usage policies. So we have to work, or that's another step that we have to take. That's another step that we have to take as far as, you know, negotiating that. Typically, you just take the more restrictive license and go with that. But DCO has like complete open access, like CC0, right? That's the policy that they go by, Creative Commons 0, right? So that we're also in the process of working on. So this is really developmental work that you're seeing, and we want to really finish this by September, October. So for data management, right? This is where we get into the citation aspects, the policies, and so on. Gemi is going to be maintained by the DCO data science team as a part of the data portal. So maintenance in the sense that we'll, if there are any contributions, we'll curate them and see how and where they should be added. We'll make sure that the people who make the contributions will get credit. We'll also maintain in the sense that the latest records will be updated for that iteratively, because there's no like automated way at this point.
You're going to do all that after the project ends?
We continue to do that. Yeah.
they're very serious about the legacy thing.
Yeah.
Yeah.
I mean, this is,
It's a huge community. It's like a 1,500 something plus scientist community around the world, and
But there's no current support infrastructure for that, right? It's just
I think it ends soon. Yes. I'm not sure. Peter's watching somewhere and commenting somewhere. I don't know.
okay.
Yeah. No. So
the questions you're asking have been thought of since the very beginning.
Yeah, I know. I mean, part of data.rpi.edu is part of the answer to that, but
Yeah.
that's really keeping the data up.
Right.
I'm not sure that that's like doing the curation,
Yes.
figuring out where it goes. I mean, this is human skill,
that
human
is
labor.
very much so. Yes. So I think there's a protocol in place. I just don't know what the exact protocol is for me to like tell you. No.
Yeah, fine.
But there is something in place for that to continue, because we were going to be involved in maintaining this for the community onwards. That's like, yeah, that was decided. And yeah, so as I mentioned, Gemi as a whole follows the open access policies, so all the contributions will follow the open access policy set by DCO. But if we retrieve data resources in large chunks, as we did from existing organizations, then we'll follow the more restrictive of the two, whichever policy they set, and then we'll try to negotiate something there. So that's where we are now. The citation policy for Gemi is where we're like, so data citation as a concept. Most of us are familiar with it, right? Anyone not familiar? Yeah, cool. So it's just, you know, we want to ensure reproducibility, that everyone gets fair credit. We also want to make sure that like data has to be cited as a first-class scientific object, just like any papers, books, or any other scientific resource you might want to cite. So unique identifiers are used for that. We use DCO IDs as unique identifiers. So this is how we're planning to work this out for Gemi. Gemi itself is identified, given a DCO ID as a whole. Each contribution will be also given a DCO ID, so that if people want to cite their contributions on resumes or any places where they've contributed a resource, they can cite that. The original resources assigned are also, oh, I'm missing words, never mind, are also given a DCO ID. And so if people only want to use the original resource, they can use the DCO ID for that. We're doing this because Mendat and RUF don't exactly have unique identifiers yet. So we're just providing them one so that the citation system will work. Other than that, for usages, we've been contemplating, like there's already established precedent for Sparkle queries having IDs, right? So unique identifiers. So when people want to use the unique IDs, they'll just query and use the unique identifier for their Sparkle query, which is essentially translating to a chunk of the data. And they'll cite the GEMI resource as a whole as well. So for reproducibility purposes, if that unique identifier will work perfectly because you know exactly the query that was run to retrieve the data and use in your analysis.
So it's sort of like a stored query in that sense.
Yeah, it's kind of like that. So that's what we have in place now. We're having discussions to see like whether we can do nested queries, nested unique identifiers and so on. But that's a discussion that's ongoing.
If you looked at, so the DOI people did a lot of discussion with application profiles and stuff like that about sort of sub-identifiers.
So I haven't looked at that in that much detail, but I know there's existing research on that. If we're going to use DCO IDs, I don't know if there's like, we are able to do that in the code yet, or we have to implement.
Well, it's handle system stuff.
Right.
So, I mean, I don't know. So the DOI people in creating application profiles, they went a little bit further in terms of thinking through it than I think the publishing industry actually wanted.
Mm-hmm.
But there are other industries that have adopted the DOI model, such as the movie industry, which may have the sub-identifiers to the extent that you're looking for.
Mm-hmm. Okay.
But if you got questions, let me know because
because
I've got the contacts at CNRI and sure. I could find this stuff.
So I'll email you. We can talk about this. This will really be helpful. Yeah. So I've already talked about this in the previous slides a little bit, I guess now. But yeah, contributions. So GEMI, we want it to be a constantly up-to-date data legacy, and contributions are welcome. Anyways, as a part of DCO, the DCO Mineral Challenge, people are going out and finding new minerals. So updating those records directly into GEMI will be like pretty good, and it will add to the GEMI data resource and the valuable nature of GEMI. So contributions are welcome. We aim to improve completeness because the data set is never really complete. You keep adding to it, but it's like a faraway goal that you try to keep getting to. And the quality of the data, which I'll discuss in like the evaluation section. I was like, we actually came up with like some semi-subjective metrics on how to evaluate a data resource. So that's also going to be part of this GEMI, but also can be generalized outside. So contribute. Yeah.
So I'm really interested in the evaluation criteria.
Sure, yeah.
Maybe Stan, Pointer, and Paula. But then I also have a question. What if when you're doing an update, there's some like split of a mineral? So this thing really is not classified as X anymore. Now it really is Y.
Yes.
Then what?
So from versioning, right?
Yeah.
Perspective, how you maintain multiple versions. So far, our philosophy on versioning has always been to keep multiple versions with multiple IDs so that people can access a certain version of the data set when they use it. We're going to continue to do that. We don't have like a method in place. The method's in place. The code isn't in place yet to do that, but that's what we're going to be following, like for the versioning.
Yeah, but that's just a version. So what if, I don't have a mineral example, but what if I had some class and now there's two subclasses, and we previously said that this sample was the superclass, when really it should be the subclass.
I see.
So it gets further refined, and then a nastier problem is, what if it was misclassified before?
I see. Okay.
So there's there's monotonic, like just more information, and then there's different information, and what you have is actually wrong.
That's interesting. I haven't thought about that yet. I know that problem comes up a lot. We were going with the assumption that the classification given was like by all the experts. So that, yeah, no, I know it
But
changes.
like
It changes.
Pluto, take Pluto,
Well,
you know,
Yeah,
it's not a
exactly.
planet.
Well, I mean,
Yeah, I know.
there can be misidentifications, but ultimately, when you do mass spectrometry and work out the actual mineral composition, then there's no question at that point, unless somebody messed up with the mass spec, I guess, but.
No, it's you're right, but I understand Deborah's question because paragenetic mode is a classification mechanism that mineralogists came up with based on primary, secondary mineral features, whether it's igneous, metamorphic, or sedimentary, and those classifications might or might not change. I understand the question. I'm trying to think of, so don't believe I've thought of that or even addressed that so far. It's just definitely.
This is a question that I think maybe applies to that. Right now, the access is to either the mineral or the locality.
Mm-hmm.
So is there work going on to access in other ways? For instance, locality, and just in looking at some of that, it says a lot about, it's an ore body of some sort. So it's a particular kind of a mineralization.
Mm-hmm.
And each mineralization has its own characteristic mix of types of minerals in it. And you can sort out a lot of these problems simply by having, a higher level access where you have 4 or 5 different terms in there to do your search.
Yeah, so far we haven't really implemented anything else other than the 2 implementations, the 2.
That's why
but it's a good idea. Yeah, it's something to think about. But it seems like the resources that we got were always starting at these 2 highest levels,
Sure.
which is why we started at them. If we were to start at other geological parameters for entry level, it would still be the same as a mineral browser. You would just classify by another geological parameter and still eventually see a mineral at a time. Your data point ID would still be.
As you pointed out right at the beginning, this is really being driven by the rock hound, the mineral hunting community. Mm-hmm. And is there a role in here with the mining companies and resource companies?
On and off. Like we've done a few panels and seminars and stuff and workshops where a lot of these we call them industry, right? Industry representatives come sit in. So there are collaborations that are formed with a particular goal in mind, and once that goal is achieved, where the project kind of ends there. One example, not really mineral related, but oil related, was to say where can we find oil resources in Ohio versus petroleum resources, and that's the one goal. So that's how those things typically work.
Well, with the issue with this higher level of understanding of the overall mineral occurrence, that's obviously important to the mining community, but would also be important to the mineral hunters as well, because there's certain types of occurrences that always have these 5 minerals.
Sure.
And if they look around and say, well, here's something that looks like the same kind of occurrence, but we only got 4 of the 5.
So yeah.
So now they know exactly what to go to look for.
We're working on that too, which it's just in an example slide because that was talks I given earlier. But part of that is part of this association rules mining project that we're doing, where it's exactly kind of what you're doing is we're trying to find, these 4 minerals occur here, and our data tells us typically this 5th mineral always occurs with them. What's the probability of that occurring? And that helps go find more things. And on that same line, so the association rule mining project only focuses on what mineral you can find, not on the abundance of the mineral. That's a different problem. This is for collectors and scientists finding mineral samples. But on another project, which I just remembered, which we did with the USGS, was predicting abundance of mineral resources or ore resources available. Yeah, if you guys remember things I'm forgetting, shout it out, because I might not remember everything. So
it's like a peanut
they're
gallery.
nodding as I'm remembering.
Yeah,
so
yeah.
Shout it out.
Anirudh says something, they go.
So they wanted to find where can we find a lot of gold, where can we find a lot of this, right? And the USGS, one of the projects was that. So that's also being worked on, but all using this data and other data sets similar to this, but not open source. There was an SNL data set, a Canadian Geological Survey data set, which is very well made as well. So we're using multiple data sets to do it, but not all of those data sets are open. Those are given by companies and you just use them and do it. So whatever is available to us, we're trying to put it in under this GEMI, which includes all earth minerals and all the information about it. So far, these are the two implementations, but sure, there'll be other entry points. We'll think about it and get to that, yeah.
So I would just wanted to loop back to sort of a comment on the versioning. Why it's important is there is, today there's a particular version of these tables. Okay, scientists go and write their papers based on that particular, and they've got all their embedded data IDs and all that happy stuff, and then things get revised. Okay, and it's really important that that anyone who is trying to reproduce that work sees what that original scientist sees. That original version has to be intact.
Absolutely.
It can indicate that the subsequent versions happened, but they have to understand that it has to be clear. And somehow also there has to be some indication for anybody coming in when they're looking at works based on this, which you didn't really show.
Scott.
Okay.
Thank you for the segue. No, so I wasn't really going to show a lot about this because I've talked about this extensively. I was going to show this, like a whole list of papers that have been published, and then keep throwing titles in your face.
Yeah, we get it.
Yeah.
Don't worry, you get credit for it. Don't worry.
No, so that's
You're fine. You're part of the DCO freight train. We get it.
So some of, other than the already published work, there's a lot of ongoing work as well. Like a couple of examples, those are co-occurring mineral, cobalt minerals that we're looking at. These are abundance of minerals found through time based on the chemical composition and the redox state, the one that's animating. There's the copper network that I've already showed multiple times. This is the association rule mining project. This one is part of the carbon mineral challenge. This one is interesting, where you have a trend of occurrences of minerals, and you're able to project how many missing minerals there are yet to be found in the world. So Greta Heisted, one of our collaborators, so she published and she predicted a quantified number of how many more minerals there are to be found. So those kind of things. There's also that LDL project, which Feifei is working on, which is a small data project. So that's a different data science challenge that we're also tackling, which looks at predicting chemical compositions of minerals, both mainly Mars minerals, but also Earth minerals, because that's what we're using for training, based on the unit cell parameters that exist. So, did I explain that? Did I just move on? No interest. That's fine. So there's a lot of stuff going on, which is really interesting and really is driven by this data resources that we put together. And
could you just so you have talked about the network analysis stuff before, but could you just briefly, so the middle one there is the copper network.
Copper network.
Yeah. Could you just briefly give a sort of a highlight of that?
So the copper network, this is a unipartite network, only one kind of node. The copper network uses copper minerals that co-occur with each other. So if two copper minerals are found in the same locality, or in this case, that's what we're using, or even any other parameter that you choose to, found in the same, have the same age, have any sort of similar geological parameter that are acting together, we form a line between them. So that's how the network was created. Typically, the analysis that we do is based on the network layout, which I established last couple of talks, was based on force-directed layout. So the network geometry itself shows you some embedded information in it. So for example, so you see reds and blues are forming a group, and then after the blues, the yellows are there. So the colors here are, if I remember correctly, are based on presence and absence of hydrogen and sulfur. And so it's like, doesn't have sulfur and hydrogen, has hydrogen, doesn't have sulfur, has hydrogen, has sulfur, doesn't have hydrogen, and then has both. And so anhydrous, hydrous, this kind of distinction between minerals, and you see the trends there. And typically the layout of the network means the things that are furthest away are like very orthogonal to each other. They are very unrelated to each other. Things that are nearby have similar geological parameters. So that's one analysis that we do. The other thing we do is run local or globalized metrics. So if I run like metrics like betweenness centrality or homophily on this network, I'll get a sense of which are the nodes that are the most like. Betweenness means that it's seeming two seemingly very distinct groups are connected by one very important node, and that importance increases. So you'll find out those kind of nodes which are hubs in this network. Or with homophily, any part of the network, if you run homophily or assortativity, it will tell you how homogeneous or heterogeneous the network is. Thereby, it will lead to more exploration. This one in particular I mentioned earlier was used in our fossil networks, where we were able to find that at any given instance of time, the fossils found in the world, the number of species existed in the world, how homogeneous they were all of the similar species, were they very different from each other. That also helps us make further insights on what kinds of taxonomy or taphonomy, which is preservational biases that exist. So things like that. So those kind of analysis are done. Other than that, also community detection, which is basically clustering for networks. Very many supervised and unsupervised methods that we apply on the network that were used to get insights. So that's just another elaboration.
Cool. No, that's what I was looking for.
So never wanted to talk about that already. Never mind. So this is like, I kept this very initial because this is also good for discussion. I didn't throw in any of the definitions I had in place, but the evaluation here is basically talking about how to evaluate a data resource in general. Surprisingly, there's not a lot on there, like literature-wise, because everyone seems to do it differently. So I wanted to put together a few metrics that have been adapted from existing fields like software engineering, usability testing, and so on. So let's start with this. These three metrics, completeness, fitness for purpose, and fitness for use, are very commonly used for data and outside. And so these are pretty clear. So completeness is just based on how many minerals exist, how many of those samples do we have, and how many columns of those are covered. So this is a fairly easy thing to quantify and calculate. You'll never really reach a complete data set, as I mentioned, perfect completeness metrics, but it's something you build towards. Fitness for purpose, it's how it is used for the intended purpose, how well it is useful for the intended purpose. And fitness for use is for a particular use case which may not be aligned with the original purpose. So like a good example to show is this paper, which we published, which is in the this was not a mineralogy study. Instead, it was a microbe study, microbiology study based on, so microbes are feeding on certain cobalt minerals to metabolize. And so we used mineral data from here to help with that analysis and get insights. Basically, we found how much of an effect the global oxidation events had on the creation of new minerals, and how the creation of those new minerals changed the way the microbes metabolize in the Archean eon.
Are some of these people deep life people?
Yeah, Eli is deep life. Jihua is a geochemist, correct? Yeah. And me and Paul, Ben is another microbe and deep life person. Mike Meyer is a paleontologist. Bob Hazen is a mineralogist. Yeah. And Paul Fokoski is also.
Yes.
Everyone knows him, I guess. Yeah. So this is like a pretty good example of fitness for use, which was not for the original purpose that Gemini was created, but it really helped.
But that's really cool.
Yeah.
I mean, because that's kind of what the whole.
So we plan to track, fitness for use, because we want really this to be used outside the, known use cases and things that it was set up for.
Fitness is in the eye of the beholder.
Yeah, exactly. So we plan to track this. So based on Nielsen 94's usability textbook, right, usability engineering or something, he had for a user interface, he said these are good metrics. He had 5 metrics. 4 of the 5 I found really useful in the context of a data resource. So learnability was. Slide again. Never mind.
Severe needs to look at this exact slide.
That's a good point to work on.
Yeah.
So learnability was how easy is it to learn to use the interface for Gemini. So that's more from a data resource access point of view. Efficiency was how efficient is it to get the exact kind of data set that you want from Gemini using the interface. Errors are how many errors there are in the Gemini data set. Are there any contradictions? Are there any, inconsistencies, whatever, any errors that might be there in retrieval or in the actual data point. Satisfaction, how well, I guess it's self-explanatory. How well satisfied are you with the data format that you got, the exact data that you got from the query? Is it working fine? Are there any missing data points? Any of these? Now these I added myself. These are my contributions to what I think are really important towards what evaluating a data resource, right? So first is readability. I phrase this as readability in terms of machine readability. So how easy is it? A perfectly readable data resource would just require no checking or exploration. Just load it in, start using it for your analysis. It should be completely machine readable, no issues, no inconsistencies, no format issues, nothing whatsoever, right? So how machine readable is it? Are there chunks of texts in certain columns that have to be delimited more? Are there any more steps you need to take, so on? Second was analyzability. This is sort of it's a very broad thing where it connects with the fitness for use. It's like, how well does this data, GEMI data resource, work for the analysis that you have in plan? So certain columns might work really well for simple regressions. It might not work for certain kind of other analysis that you plan to do. If you plan to do network analysis with certain columns of the data, it's not going to work that well. So the analyzability goes down. So obviously the more robust the analysis is, the analyzability will be in question. So if you have more geological parameters with fewer missing values, with the right formatting, and all the parameters are equally important for the analysis that you're trying to do, the analyzability of the data set will go up high. So that's sort of the broad idea behind it, to say like, how well is it useful for data analysis? Not just the machine readability, not just efficiency or whatever. So because every data set has to be used for some analysis or something, whether it is just simple loading it up into Excel to produce a visualization.
But it's kind of like your criteria is going to be dependent upon the particular kind of model that you want to.
Yes, so this would cover the fitness for use. In complement of the fitness for use, this would cover how many different use cases is this used for, and how many different use cases is this useful for well. So it's able to answer that additional questions, like even though it's able to answer diverse questions in diverse fields, how well is it able to do in those diverse fields? Is it just barely useful, or is it actually useful when you're doing analysis? So the names are pretty like iffy. I just threw whatever terms I thought were best, but I have the definition out in the paper, which is in prep. It's going to be probably submitted soon.
Funky. It's like, is it going to throw an error if I do a PCA on it?
Yeah. So it's in the simplest sense, but yes.
Yeah.
So and the last one
we scaled it for you. We're not
so the last one is entropy, which is just information entropy in terms of what are the uncertainties that exist in the data set. This is more subjective than some of the others because a lot of the uncertainty in the data set will be documented as part of the information page, right? What contributions came from where, and a combination of all the metrics previously mentioned will help you know what's uncertain.
Did you look at Stefan's stuff on data quality?
I did, yeah. I did. And so to end off with that, right? So Stefan's work on the data quality labels and work I did with Stefan on the dark data for analyzing ontology quality and so on. All of these metrics are going to be in a TRL like technology readiness level like scale. So they're going to be, users are going to be giving us these metrics in that scale, and we have them defined for the ontology purpose. We're going to adapt the ontology TRL readiness type thing onto this, where we have scales of scores they can set, and they would have more meaning than just an arbitrarily set, a 7 or an 8, Cool. So this is going to have much more meaning than just a random score thrown there. That's what I'm going to use. So that's also work we did previously. So I'm using all the stuff here.
Yeah. That is very cool.
Yeah. So
that data quality label stuff, when people first see it, they're like, wow, nutritional facts for.
Oh yeah. See, yeah.
Yeah.
Store, I think.
And then you go like, oh,
Your mileage, but vary.
Yeah, well, that's exactly it. I mean, fitness is in the eye of the beholder. Data quality is in the eye of the beholder.
Yeah, it's highly subjective, but
And he
it's
picked
good
like
that
a
it's subjective sometimes.
fantastic example.
If it proves your hypothesis, it must have been good data, right?
So let's thank. Any other questions?
So in terms of the versioning questions that were asked, I'm thinking in terms of the dynamic data citation work that we did over the summer. So we do have some things worked out within the DCO as to how that, so if you come back and want to query, find an exact data set, even though it's been repurposed or, classes have been realigned, you can still get that exact data set for that particular experiment.
Yeah, this is part of the RDA
Yeah.
recommendations, right? Yeah.
Right.
So the
Yeah.
RDA has a set of recommendations. Brenda, Ahmed, Shweta, we're all working on it last summer on putting together like what RDA recommendations are we going to adopt into DCO and implement in. So quite a few of them have already been implemented,
Yes.
which we can use for Jemmy because it's going into DCO data portal. So yeah,
So-
thank you. Yeah.
So this general sort of approach, so other parts of DCO, such as like other data sources like VAMPs and stuff like that, have similar approaches been used to kind of stitch that stuff together?
For VAMs,
Well, I mean, I
yeah,
use
yeah.
VAMPs as an example. But
Yeah. So
Nightmare?
no, sure.
because so,